Hello students, welcome to class 12 physics. In this video we are going to discuss about the LC circuit and LC oscillations of chapter 7 alternating current. First of all, let us understand what is meant by LC circuit and what are LC oscillations. So here the name clearly suggests itself that LC circuit means here the inductor and the capacitor are connected. So we can say a circuit in which inductor having the negligible resistance is connected with the capacitor. Such type of circuit is known as LC circuit. When a charged capacitor is discharged by inductor having negligible resistance, the electric oscillations of constant amplitude and constant frequencies are produced. Such type of oscillation is known as LC oscillations. So first of all, you note down this LC circuit and the LC oscillations. Then we will be seeing the details of that each circuit as well as the derivation of LC oscillation. Now let us derive the differential equation for a LC circuit. LC circuit is shown in figure. In this circuit, capacitor C and inductor L are connected. So here you can see we are having a capacitor and an inductor that are connected with each other and completes the circuit. Let at time t equals to 0, capacitor is charged and charge on it is Qm. That means initially let us consider the situation where the capacitor is fully charged. So we are taking at t equals to 0, capacitor is fully charged, and in that time Q will be equals to Qm. That means the charges on the capacitor will be having the maximum value, that is Qm. The moment the circuit is completed, the charge on the capacitor starts decreasing, giving rise to the current in the circuit. That means when this capacitor is fully charged and when the circuit is open, the charge will not be flowing in the circuit. But as soon as the circuit is completed, as soon as there is the closed path, then the charges from the capacitor starts to flow in the circuit, and this flow of charges is called as the current. So the charges on the capacitor starts decreasing, which we call it as discharging of the capacitor, and this discharging of the capacitor gives rise to the current. Now let Q and I be the charge and the current in the circuit at time t. Since di by dt is positive, the induced EMF in L will have polarity as shown in the figure, means VA is greater than VB. So here the potential at point A is greater than potential at point B of the inductor, because here the current keeps on increasing. As Q decreases, I increases. So we can write I equals to minus dq by dt, because we have seen in the situation that the fully charged capacitor, it will start discharging. That means the charges on the capacitor keeps on reducing and there will be flow of the charges. The flow of the charges will be more, giving increase in the current. So Q decreases and simultaneously I increases. So we can write the equation as I equals to minus dq by dt. Now induced EMF in inductor at any instant, EMF that is equals to minus L di by dt, and the potential difference across the capacitor that is equals to Q by C. So now let us start with this circuit, that is the capacitor. So voltage drop across the capacitor, that is VC. Now let us choose this path, that is the clockwise direction. As the path and the current both are in same direction, the sign will be negative. Then we come across inductor. So potential difference across this inductor, that is equals to VL. Now the circuit is completed, so it is equals to 0. Here VC is nothing but Q by C minus VL is nothing but L di by dt equals to 0. So we get this equation. We are having Q by C minus L di by dt equals to 0. But here we know that I equals to minus dq by dt. So, and again taking the derivative of I with respect to t, we get di by dt equals to d by dt into minus dq by dt, that is equals to minus d square q upon dt square. So using this equation di by dt, in this equation we get minus L into minus d square q upon dt square plus q by c equals to 0. So minus minus becomes plus, so we will be having L d square q upon dt square plus q by c equals to 0. Now taking L common from both the terms, here there is no L, so multiply divide by L. Now we take common L, so it will be d square q upon dt square plus q by Lc equals to 0. When we take this L over here, then it will be 0. So now it will be d square q upon dt square plus q by Lc equals to 0. Here let us take 1 by Lc. 1 by Lc equals to omega 0 square. So d square, this equation becomes d square q upon dt square plus omega 0 square q equals to 0, because 1 by Lc equals to omega 0 square. Now this equation can be compared with the equation for the linear charge, that is the linear charge differential equation, d square x upon dt square plus omega 0 square x equals to 0. So here you can see, instead of x we are having q, and instead of this, that means x, instead of x we are having q over here. So this equation has the form of general formula for a simple harmonic oscillator. That means these equation we have studied differential equation for the oscillations, and the same type of differential equation we are having for the LC oscillator. So the charge oscillates with a natural frequency omega 0 equals to 1 upon root LC. Now omega 0 is 2 pi f0 equals to 1 upon root LC. Taking f0 as subject and taking 2 pi over here, we get f0 equals to 1 upon 2 pi under root 1 upon LC. So students, you may note down this theory. Solve the differential equation of LC circuit and obtain the expression of current. The differential equation of LC circuit that we have already seen, that is d square q upon dt square plus 1 by LC q equals to 0. The solution of this equation, it is q equals to qm cos omega 0 t plus phi, where qm is the maximum value of q and phi is the phase constant. Now at t equals to 0, q equals to qm. because here we have considered that initially the capacitor is fully charged. So the charge on the capacitor has the maximum value, which is equals to Qm. So at t equals to 0, Q equals to Qm. Therefore, from these equation, Qm gets cancelled and 1 equals to cos phi. Cos phi equals to 1 we get when phi equals to 0 degree. Therefore, from equation 1 we can write Qm cos omega 0 t, because here phi equals to 0 degree, so equation becomes Q equals to Qm cos omega 0 t. Now differentiating this equation with respect to time, we get, taking derivative on both the sides, we get dq by dt equals to d by dt into Qm cos omega 0 t. Now here taking Qm outside, we get d by dt cos omega 0 t. Now derivative of cos omega 0 t, that is minus sin omega 0 t. So that can be written as Qm minus sin omega 0 t, and from these omega 0 t again derivative of that will be omega 0, so into omega 0. So now equation becomes Qm omega 0 into sin omega 0 t, that we can see over here. But dq by dt, that is equals to minus I. So the left hand side equation becomes minus I, and on the right hand side we have minus Qm omega 0 sin omega 0 t. Minus minus gets cancelled. We have I equals to Qm omega 0 sin omega 0 t. Now taking this Qm omega 0 as Im, we get I equals to Im omega sin omega 0 t. Here we have taken Im equals to Qm omega 0. Thus, the equation of the current for the circuit is I equals to Im sin omega 0 t. So, for the LCR circuit, we are having two values, two equations, that is Q equals to Qm cos omega 0 t and I equals to Im sin omega 0 t. So, students, you may note down this theory. Now explain how LC oscillations takes place in the circuit. So figure shows a capacitor with initial charge Qm connected to an ideal conductor. The electrical energy stored in the charged capacitor is U equals to half Qm square by C. So initially what we have taken, that the capacitor is fully charged. So the electrical energy that is stored in the capacitor will be half Q square by C. Here initially it is fully charged, so the charge will be having the maximum value. So we are writing half Qm square by C. Since the circuit is open, there is no current in the circuit. The energy in the inductor is 0. So as you can see over here, that current is 0. The circuit is open, so no current is flowing through the inductor. Thus, no flux is generated, and thus the magnetic energy through the inductor is 0. Thus, the total energy for this LC circuit, which is the electrical energy plus the magnetic energy. Here magnetic energy is 0, so total energy is equals to the electric energy, which is equals to half Qm square by C. Now at t equals to 0, switch is closed and the capacitor starts to discharge. This is shown in figure B. As the current increases, it sets up a magnetic field in the inductor and thereby magnetic energy stored will be UB equals to half Li square. Now as you can see over here in this figure, now the circuit is completed. So now the charge on the capacitor gets discharged. That means the charge on the plates of the capacitor will be moving along this path, generating the current. So here on the plate of the capacitor the charge decreases, thereby the current will be increasing. This current when flows through the inductor, the magnetic field will be generated. Thus the magnetic energy stored in the inductor will be equal to half Li square. So we can say here in the capacitor as the charges are decreasing, the electrical energy will be decreasing. On the other hand, the through the inductor the current increases, thus the magnetic energy also increases. As the current reaches its maximum value Im at t equals to t by 4, all the energy is stored in the magnetic field UB equals to half Lim square. This is shown in figure C. So here we can see in the figure C that now all of the charges that were deposited on the plate of the capacitor, now they are being removed and the current that is flowing is the maximum current. There is no charge on the capacitor, so the electrical energy will be 0. Now the current that is flowing through the inductor, that is the maximum current. So the energy, the magnetic energy stored in the inductor, that is equals to half Lim square, because here the current is maximum, so the magnetic energy is half Lim square. Since maximum electrical energy of capacitor equals the maximum magnetic energy from the inductor, the capacitor now has no charge and hence no energy. The current now starts charging the capacitor as shown in figure D. This process continues till the capacitor is fully charged at time t equals to t by 2 as shown in figure E. But it is charged with a polarity opposite to its initial state as in figure A. So as you can see over here in this figure, when there is the maximum current through this inductor, this current now starts charging this capacitor. But now the polarity will be reversed. That means initially the plate which was negatively charged, now it becomes positively charged, and the one which was positively charged becomes now the negatively charged. So again now the current keeps on decreasing, and on the other hand the charges gets deposited on the plate of the capacitor. So now the magnetic energy decreases, on the other hand electric energy increases. So this process continues. The whole process just described will now repeat itself till the system reverts to its original state. Thus the energy in the system oscillates between the capacitor and the inductor. Here the system that consists of the inductor and the capacitor, we have seen that initially the electrical energy is maximum and the magnetic energy is 0. Slowly and gradually the electrical energy decreases and magnetic energy increases. There will be a time where electrical energy will be 0, magnetic energy will be maximum. Now the case will be reversed. Magnetic energy decreases and electric energy increases. There will be a time where electrical energy will be maximum and magnetic energy will be 0. So it oscillates between the two levels, between two energies. Hence the charge between two plates oscillates by inductor. This phenomena is known as the LC circuit. So students, you may note down this theory.